And thank you so much to Anne-Marie's group and the organizers for inviting me. It's so nice to be back here. It really doesn't feel like coming home. Okay, so hopefully that flickering isn't going to keep happening the whole time. But in any event, so my talk today is going to be about dark matter, which of course is one of the largest remaining mysteries that we have in astronomy. And specifically, I'm going to start off by arguing that the Milky Way is actually our most important laboratory for studying dark matter physics. I'll then get into a little bit the implications of what actually changing your assumptions about what dark matter is made of changes a Milky Way-like galaxy. And then as a case study, I'll get into some work I did over the last couple of years with the wonderful folks listed on the slide here, using the interaction between the Milky Way and one of its satellite galaxies to try to constrain the nature of dark matter. So I'll take away this text here and introduce you to our laboratory, the Milky Way. Hopefully at least some of you have seen this gorgeous image from the Gaia spacecraft showing all the stars that it's currently tracking in the Milky Way. Of course, the Milky Way's disk stands out very prominently in the center. And then surrounding the disk, there's of course the stellar halo. It's this very diffuse sort of spherical collection of stars that surrounds the disk of the galaxy to large distances. And then what you can't see in this image is the dark matter halo. So this big cloud of dark matter that the rest of the luminous galaxy is embedded in. And that of course makes up the vast majority of the mass in the Milky Way. So you'll also see in this image a couple of the Milky Way's satellite galaxies. And these, of course, live inside their own clouds of dark matter. We call these subhalos because they're smaller dark matter halos embedded inside large ones. And in particular, I'll draw your attention to this one. This is the LMC. It's the Milky Way's largest satellite galaxy. So it makes up about 10% or so of the mass of the Milky Way. So it's pretty big as dwarf galaxies go. And it's currently on its first infall to the Milky Way. So the orbit looks something like this in the sky, went through its first pericenter passage about 60 million years or so, give or take. And I mentioned the LMC specifically because, as I'll mention throughout the rest of the talk, it has a really big influence on what the dark matter in the Milky Way is doing. So if you're doing these kind of dark matter experiments, it's really important to take the LMC into account. Okay, so that's our laboratory. And now what about our research subject? That would be dark matter. And I think dark matter is a really interesting thing to study because it seems like we know a lot about it on one hand, and on the other hand, like pretty much almost nothing. So what I mean by that is if we start with a very simple set of assumptions, namely that dark matter is collisionless, it's cold, and it only interacts with luminous matter via gravity, we can plug those assumptions into a simulation and get something that looks, on large scales at least, very much like our own universe. But at the end of the day, we still have absolutely no idea what kind of particle actually makes up this dark matter. And so to give you a sense of the sort of depth of the problem here, here are a few different candidates for dark matter particles placed on this mass scale. And you'll see this spans over 30 orders of magnitude, all the way from tera electron volts down to like 10 to the minus 21, sometimes even more EV. So there's a lot of parameter space to search here. But eventually, of course, what you'd like to do, the end goal of all of this would be to actually find a dark matter particle, directly detect one, because then you know what you found. And so particle physicists spend a lot of time and effort and money into devising various kinds of detectors to find an interaction between a dark matter particle and a baryon, but they haven't found anything yet. They haven't detected any dark matter particles. So what that really means is that all of the evidence we have for both the existence and the nature of dark matter comes from astrophysical probes. And in particular, the Milky Way is our most important site for doing these kind of astrophysical probes, because if you're doing the probes in the Milky Way, you can use that to inform the design of your direct detection experiments. That makes sense, right? If you have a dark matter detector on Earth, it's in the solar system, you'd like to have some idea of what the dark matter in the solar system is doing, you can build the right detector. So to give you an example of this, I'll pull up this plot here from a study my advisor, Bettina Vesla, did a few years ago, This is showing the velocity distribution of dark matter particles in the solar neighborhood. So the contribution from the Milky Way is this dashed blue line here, and the contribution from the LMC is this solid histogram. I will point out that's normalized, so the LMC contributes a lot less dark matter than the Milky Way does, but you'll notice it's all at much higher velocities. And that has the effect of shifting the tail of the combined distribution in red up just a little bit. You might say that doesn't look like much, but if we actually take this a step further and examine the consequences for direct detection, this is a study by Smith-Orlick et al., who looked at sort of Milky Way LMC analogs in cosmological simulations. And so what I'm showing here is the cross-section of interaction between a dark matter particle and a detector. So the higher that is, the easier it is to detect the dark matter particle versus the dark matter particle mass here. And I'll draw your attention to the difference between the black line, which is an isolated Milky Way galaxy, and this solid orange line, which is a Milky Way LMC-like pair. And so especially in the sort of zoomed in panel here on the right, you can see the difference between these two lines is in most cases many orders of magnitude. And so that's really going to alter the conclusions that you can draw from a direct detection experiment. So the infall of a massive satellite like the LMC and knowing how that affects the dark matter in the solar system is really important to make sure that your particle physics experiments are drawing conclusions. So that's one reason why the Milky Way is really. The second is because of the fidelity of the observations we have in our own galaxy to actually place constraints on our models. So this is an example of just a handful of facilities that are currently taking really wide field surveys of the stellar halo in the Milky Way. And in particular, it's this sort of synthesis between astrometric surveys like Gaia with spectroscopic surveys like DESI that are giving us 6-dimensional information of the halo. And so by that, I mean 3D positions and 3D velocities. And so that's really important because if you have a handle on how the stars are moving, you can start to say something about the gravitational potential that they're moving in. And because that potential is largely sourced from the dark matter in the Milky Way, that can start giving you a handle on what the dark matter is doing. So of course, you can't just take pictures of a bunch of stars and figure out what dark matter is. It's a lot more complicated than that. Not only do you need very precise measurements, please come back. Of enough stars to be able to actually have good statistics, good constraining power. You also need good models to constrain in the first place. So you need models that connect the kinematics of the stars that you're observing to the underlying gravitational potential, also in non-equilibrium systems like the Milky Way is. And then you also need models that explain what actually changing your assumption about what the dark matter particle is, how that imprints itself upon your galaxy. And so this is where I'm going to focus for the rest of the talk today, because this is the kind of thing that we do. So when I say changing the dark matter physics in our simulations, what actually are the knobs that we can turn? So I'm going to show you examples of a few different dark matter models that show up a lot in the recent literature. So the simplest case is cold dark matter of lambda CDM fame. It's very simple, it's cold, it's collisionless. You can just treat it with an n-body simulation, no extra physics, behaves really nicely. If we instead allow the dark matter particles some very small but non-zero cross-section of interaction with either each other or in some cases with baryons in the very early universe, we get what's called interacting or self-interacting dark matter. And then the other knob we have to turn is the particle mass. So if we lower the particle mass just a little bit, that translates to raising the sort of average velocity of these dark matter particles. It increases the length that they can free stream. We call this warm dark matter. And then lastly, if we drop the mass all the way down to where quantum mechanics actually starts becoming really important to describe the dynamics, we have what's called fuzzy dark matter. And we'll spend some more time on that in a few more slides.
A quick question.
Yeah,
When you
please.
say cross-section interaction, is that a gravitational interaction or?
It's a direct like scattering cross section for like elastic collisions. So these self-interacting dark matter particles can actually scatter with each other.
We want to be or.
It depends on the flavor you want to choose.
Okay, so I mean, does that probe the size of the particle or?
Yeah, so it probes, it can probe the mass, it can probe like sort of different physics beyond the standard model. So a lot of these self-interacting dark matter models are sort of like dark sector stuff. So we imagine that these particles, don't interact with baryons, but they interact sort of like baryons, but kind of in their own little corner, if that makes sense, so they can scatter off of each other. They have generally you invoke some kind of force carrier that works between these dark matter particles, but it really depends on the flavor.
Cool, thanks.
Sure. Okay, so when we actually turn these knobs, what happens to a Milky Way-like galaxy? Well, for warm dark matter, really the primary consequence is to suppress the formation of very small dark matter halos. So in other words, you're forming fewer low mass galaxies, fewer satellite galaxies around the Milky Way galaxy. So this is a plot from Kim et al. Showing the expected satellite mass function around a Milky Way-like galaxy. If it comes back. So cold dark matter is this dashed blue line here, and then you have different particle masses of warm dark matter. And the relevant point here is just that as you lower the warm dark matter particle mass, you have fewer and fewer small satellites around the Milky Way galaxy. Yes?
I have a very basic question. So why is it called cold dark matter and warm?
Yeah, so that has to do with like sort of it essentially comes down to the average velocity that these dark matter particles have. So cold dark matter is cold, it has very low average velocity, so it can clump together really, really effectively. And then warm dark matter is moving a little bit faster, so it has trouble making very small clumps. Like if you have big clumps with a lot of gravity, you can capture more and more of these warm dark matter particles. But because they're moving so quickly, they have trouble making like really small halos, if that makes sense. Yeah.
I have one other question related to this, which is that, does the temperature of dark matter ever change across the universe's history?
That's a good question. I think the way that we sort of currently think of it is it behaves like, other matter components in the universe. So like, yes,
But how does it get rid of, because one thing I've always thought is like dark matter halos are much larger than, say, like the visible component of the galaxy.
yeah,
And one justification I've heard for that is that, well, dark matter can't radiate, so it can't collapse down like the luminous part of the
yeah,
galaxy.
yeah. So yeah, in that sense, like most of the models that people invoke in the current literature, yeah, it's not like cooling radiatively. I mean, like, it will in the sense that like,
But is there any other
equations stay
cool?
not with these particular
Okay.
flavors, right?
Thanks.
That answer your question? Yeah. So that's what you get with warm dark matter. With self-interacting dark matter, what you're primarily doing is changing the shape of the small scale halos. So in particular, if you plot the density of a dark matter halo sort of spherically averaged over radius, in cold dark matter, it's predicted that every halo sort of follows this NFW density profile. Hopefully most of you have heard that term before, where the density rises to a peak or a cusp at the center. But what happens in self-interacting dark matter, if you let the dark matter start scattering off of itself, you'll actually destroy that density cusp and form sort of a constant density core in the centers of these galaxies. So if you measure the rotation curve of dwarf galaxies, you can get a sense of this. I would be remiss for not mentioning you can do this with star formation physics as well. So you have to be careful in your simulations, sort of disentangling those two effects. But that's the primary consequence of self-interacting dark matter. Yes.
I'm wondering about like what is the back reaction of this? Like when you have self-interacting dark matter, is there an emission of radiation when there's like what's or the
So not like
what is it self-inter like what is that?
yeah, and again, it sort of depends on the flavor. Like it's they're generally parameterized in simulations as completely elastic collisions, so there's no, like change in energy, there's no radiation, nothing like that, they're just allowed to bounce off of each other.
Okay, so they're scattered to larger radii, is that kind of like that flattening and pushing?
Yeah, so essentially what happens if you get like a lot of, if you're packing together like a really, really large number density of these particles, of course, the frequency of collisions is going to increase. And so eventually it gets to sort of this equilibrium where you can maintain balance between like the amount of scattering of particles to larger distances versus the amount of gravity that's keeping them there. If that makes sense, yes.
Do they escape, or do they just go out to large radii after they bounce around?
So I imagine some of them would escape. I mean, it's an n-body system, right? So like eventually, if you have interactions between the particles, you get some evaporation. But primarily they stay with them. Well, sometimes in self-interacting dark matter, you can get kind of like a core collapse scenario. But that's sort of beyond the scope of what I'm talking about. If you're interested, I'm around the rest of the day, we can talk about it, but. Okay, so let's talk about fuzzy dark matter now, because this is the weird one. If you weren't confused before, we're gonna spend some, don't worry, I'm gonna spend a lot more time here. So fuzzy dark matter is really interesting because the particle that makes up fuzzy dark matter is a photon, but it's really, really, really light. So these particles have masses of order 10 to the minus 22 electron volts or so. And the exact range of what's considered fuzzy kind of depends on who you talk to. But the relevant point here is that because these particles have such a tiny mass, they have almost no momentum. And that means their de Broglie wavelengths are huge, like on the scales of parsecs to kiloparsecs. And that means that even on galactic scales, they're better treated as waves than as particles. And you have to start worrying about quantum mechanics. So one of the consequences of fuzzy dark matter is, like warm dark matter, it suppresses the amount of small scale structured forms. Yes?
Sorry.
No, it's okay. I'm trying to get through a lot in a half hour, please.
Like, on behalf of any undergrads in the room who got terrified of this, could you explain what you just rapidly ran through with the Broglie wavelength?
Yeah. So, just like photons are treated as particles and as waves, even particles with mass have some intrinsic wavelength. And that wavelength depends inversely on the particle's momentum. So, for like a human, for example, at least on quantum scales, I have quite a lot of momentum, so my wavelength is completely negligible. But with these kind of particles that are really, really, really light, that means this sort of wave description of them is a lot more accurate on the scales of galaxies. Does that make any sense? I'm seeing a couple nods. Okay, cool, thank you. Okay, so like warm dark matter, fuzzy dark matter suppresses this amount of small scale structure that forms because you can't form any galaxies that are sort of smaller than the wavelength particles, right? The other consequence that you kind of get for free is it mimics self-interacting dark matter as well, and then it forms chord density profiles in the centers of these halos. So this is, this black line here is sort of a typical density profile for an FDM halo. It follows an NFW profile on the outskirts, but towards the center, it comes back, it flattens out again towards the center. So you get those chord halos for free. It's really all.
I am so sorry.
No, I'm sorry. It's like it keeps derailing me.
Okay, can I ask this very quickly? How do you actually implement this in the code?
Yeah, so I'll get into that in like a tiny bit, but like essentially there's equations of motion that you solve on a grid. So you say like each grid cell in your simulation box has like the density and the velocity of the dark matter in that cell, and then you're just solving these equations on a grid.
Oh, I was thinking particularly for fuzzy dark matter versus cold dark matter. Like,
Yeah,
what is
so cold dark matter is just a.
just n-body,
Yeah.
okay, but then you go to a grid for
For
fuzzy,
fuzzy dark
gotcha.
So the other interesting consequence of the fact that these particles are better treated as waves is, like any other kind of waves, they can actually interfere with each other. And this shows up as fluctuations in the density of your dark matter halo. So this is the structure of an equilibrium fuzzy dark matter halo. This is from the simulation by Tom Biavitz. And you can see this halo looks very stochastic. We call these little blobs of fuzzy dark matter granules. And as you might imagine, these have some pretty interesting consequences for the dynamics of stars that are orbiting in these galaxies. Yes.
Is this why they're called fuzzy?
Yeah, primarily. Also, just if you know, non-local, you can't localize the particles because they're.
Oh,
Uh,
I like it.
So what you can get in this kind of halo is actually an extra source of dynamical heating for stars. So this is a really nice study that Neil Dalal and Andrei Kratsov did, where they were looking at the velocity dispersion of stars as a function of time in like an ultra-faint dwarf galaxy like Segway 1 or Segway 2, which are Milky Way satellites. And they try out a couple different particle masses for fuzzy dark matter, they try out a couple different halo shapes, but the takeaway here is that this velocity dispersion of these stars is increasing monotonically with time. And that's only due to the interaction between the stars and these fuzzy dark matter granules. So that's one of the ways that we can sort of put constraints on fuzzy dark matter as a candidate particle. So the last really interesting consequence is that it can also mess with dynamical friction. And so for those who might not be familiar, dynamical friction is the process by which satellite galaxies lose orbital energy as they're falling into their host galaxies and eventually merge. So what happens is if you have a perturber like a satellite galaxy moving through some background of dark matter, like its host galaxy's halo, that dwarf galaxy will pull on the dark matter of the host and it'll collect behind it into this density wake that has some gravitational pull back on the satellite, slows it down, eventually causes it to merge. And so this is an example of some of those dynamical friction wakes in fuzzy dark matter from Lachlan Lancaster. So we have a fast moving perturber on top, a slow moving perturber on the bottom, time moves left to right. And again, you can see these interference patterns that show up in the fuzzy dark matter. And actually, if your perturber is moving slow enough, you can form some of the wake in front of the perturber, which can actually start pulling it forward as well. So that really affects like the drag force that a satellite would feel. Okay, this is a good time to pause for more dark matter questions before I move on. Yes.
Is the dynamic friction only a property of fuzzy dark matter?
No, so any sort of time that you have a massive object moving through like some kind of background, this can work with gas, like this, it can cause like a supermassive black hole to spiral through gas in the galaxy, works in any kind of dark matter.
So if you take, let's say, cold dark matter in this space or warm dark matter, can they also produce dynamic friction?
Yeah, so it will produce dynamical friction, yeah. The catch with the fuzzy dark matter is it's the only one that like dynamical friction can be drastically different than others, if that makes sense. Yes.
What would be your potential like observational signature of this, or is just like something?
I'm getting to that. So, that brings me now to, yeah. No, please, it's a lot I'm trying to get through in a very short amount of time.
Just a quick question. So the density profile that you got for the, I think, fuzzy dark matter, right? It basically becomes constant as close you are getting to the core.
Yeah.
Is it because like of the wave interaction of the fuzzy dark matter? Is it because of the wave nature of the fuzzy dark matter?
Kind of, yeah. So it's essentially it's forming a Bose-Einstein condensate in the center of the galaxy. So of course these particles are like super duper light, right? So you need an enormous number density of them to actually form like the mass of the galaxy. And so because they're bosons, when you start packing a whole bunch of them into a space much smaller than their wavelength, they condense. That's why you get that flat.
I don't remember those, right?
So I have a dynamics question.
Yeah.
How do you get the wake in front of the satellite galaxy that you mentioned in the last level?
Yeah, so that's entirely due to the wave interference between.
Gotcha. So that only happens in fuzzy dark matter.
Yeah, yes.
Have you explored rotating dark matter halos and what, like, if that could be a degeneracy and trying to constrain dark matter, like if you're if you're inflowing with the rotation of the stellar halo versus against it.
Oh, that's really interesting.
Sorry, that's just gonna,
No. I imagine, I mean, there's studies, right, that do this with like cosmological simulations, so they're like cosmologically assembling
Right.
halos that
Yeah,
have some
that will
rotation.
happen.
So like, that's, I guess, sort of baked into those kind of studies, but that's not what I'm gonna talk about here.
Okay.
Cool. Okay, so now I'm gonna talk about my place in all of this, the paper I wrote over the last couple of years. And this is focused on using the interaction between the LMC and the Milky Way to get a handle on whether we can distinguish between cold dark matter and fuzzy dark matter. Yes,
sorry. How do you know it's orbit?
the orbit. So
Yeah.
so we have measurements of the position and the velocity of the LMC at present, right? So then if you, you can, I mean, there's many different like layers of complexity that you can add on to this. The simplest case is just to assume a Milky Way potential and then integrate the LMC backwards in time based on its like known location. The more complicated way of doing it is to, I'll show this on the next slide. Once you have a handle on like where the infall actually happened, you can then run like a fully live n-body simulation of the LMC and the Milky Way. And then if the LMC ends up at the correct like base space position, you know, you have a decent idea of the orbit. But yes, the orbit is somewhat.
You do have to like assume some potential.
Yes. Yeah. Cool. So it's been pretty well established at this point that the infall of the LMC to the Milky Way messes up the shape of the Milky Way's dark matter halo to a fairly large extent. So one example of these kind of simulations, like these full n-body simulations of the interaction between the Milky Way and the LMC I just mentioned, was done by Nico Garavito Camargo. And what I'm going to show you here is the change in density in the Milky Way's dark matter with respect to the initial conditions as the LMC falls in. So if I play this, the first thing you should notice is this big overdensity that forms behind the LMC trailing it. That's that dynamical friction wave that I mentioned. That's what has the gravity that's slowing down the LMC. And then toward the end of the simulation, you'll also see this sort of dipole response where the density increases here, decreases here. And that's due to the inner portions of the Milky Way orbiting the common barycenter that shares with the LMC. But for the rest of the talk today, I'm going to be focused completely on the wake. Because as I mentioned earlier, fuzzy dark matter is known to mess with dynamical friction wakes. And so this gives us a very nice opportunity to constrain dark matter. Yeah.
Sorry, can I ask a question about that?
Yeah.
So this is just the dark matter.
Correct.
It's correct.
Yeah.
Okay.
And specifically the change with respect to the initial conditions. Yeah, this is full. Okay. Yes.
I don't know if you're allowed to say this, but why does the wake suddenly dissipate? Like, if you keep watching, it goes red, suddenly it's all like right there.
Yeah. So eventually what happens, like the wake, so the LMC, right, as it's coming in, it's kind of deflecting particles behind it.
Right.
So eventually, like the paths of those particles will then diverge again and will cause the wake to dissipate. The reason it gets less relatively strong toward the center is because the formation of these wakes depends inversely on the velocity. So as the LMC gets toward pericenter, the wake gets weaker, essentially.
Okay.
Because it's moving faster, so it's less efficient at generating that. Cool. Thank you for all of the questions, by the way. This is really fun. Cool. So the questions that we want to answer about this wake is, first of all, we want to know in the first place if it's possible to use it as sort of an independent probe of the existence of dark matter in the first place. So what I mean by that is we want to know whether the response of the stellar halo, the stars that we can see, is somehow sensitive to the gravity of the dark matter wake. So it's a bit of a subtle point, so I'll go through it in a little bit more detail. So let's suspend our disbelief for a moment and say that there's no dark matter in the Milky Way at all. The LMC is only falling through the stellar halo. you would expect in that case to still see a wake in the stars. It's the exact same physics that produces the dark matter wake. So the question is, if I add the dark matter, this dark matter wake now has some amount of gravity. That's what's responsible for slowing the LMC down. So if we can show that the stars also react to the gravity of the dark matter wake, then we know that when we look at the stars, there's information there about what the dark matter is doing. And it's not just due to the LMC alone, if that makes sense. That's the first question we want to answer. And the second question is to take that a step further and say, okay, if we now make the wake out of fuzzy dark matter instead of cold dark matter, does that change anything about the wake? Does that change any observables? Can we use this scenario to distinguish between the two? And so the setup we're using is something I like to call a dark matter wind tunnel. So we're working in the rest frame of the LMC. And we start with a periodic simulation box, and the LMC is just a externally imposed Hernquist potential that just stays at the center of the box throughout the integration. And the dark matter and the star particles are this homogeneous background that we give a velocity boost. So it flows past the LMC, and we can study the wake that forms downstream. And so there's 5 different sort of parameters we can tweak with this wind. That's the density and the velocity dispersion of both the stars and the dark matter separately, and then the bulk velocity, which is shared by both species. And we tune these such that the wakes in this wind tunnel look as similar as possible to the wakes in Nico Garavito-Camargo simulations that I showed a couple slides ago. And then we're going to run this back. Sorry about the blinking. With 3 different assumptions for the dark matter physics. So we have cold dark matter, both with and without gravity from the dark matter particles. So that gives us a sense of whether the self-gravity of the dark matter matters for the formation of the wake, and it also gives us a sense of whether the dark matter wake's gravity matters for the stars. And then we use fuzzy dark matter, again, with self-gravity to compare against cold dark matter. And so here's what these wakes look like. So what I'm showing you here is the density contrast in the midplane of our simulation box. So the little cross there shows you where the LMC potential is located. And then the wake shows up as the overdensity downstream. So this case on the left here is cold dark matter without self-gravity. And I should mention this is just the dark particles for now. So the only gravity on these particles is from the LMC. They're not interacting with each other. If I then turn on the gravity between the dark matter particles, already you should see a difference. So this white contour that I'm using to define the wake boundary, we set that to half the maximum density in the right panel. So you can just sort of read the full width half max of the wake off the plot. And we set it to cold dark matter with self-gravity always, because that's the sort of fiducial case that we're comparing the others against. So the takeaway here is that not only does the gravity of the dark matter wake keep it together for a little bit longer, it gets about 50 kiloparsecs longer, it also increases the maximum density by about 10% or so. That's consistent with some earlier work using linear response theory by Simon Bergier. But that's just the dark matter. What about the stuff you can see? What about the stars?
We can't see it.
So, cold dark matter without self-gravity, again, here on the left. So again, I want to really hammer home here that this is the only gravitational force on these particles is from the LMC. This is the wake that would be formed in the stellar halo if dark matter did not exist. Okay. If I let the stars then feel the gravity of the dark matter wake, again, we see a pretty good difference here. So it's a similar sort of scenario as with the dark matter particles. The wake gets longer by about 50 kiloparsecs, and you raise the density by about 10% or so. And so that's great. That answers our first question. We know that the wake in the stars does contain information about what the dark matter is doing, which is really cool. That means we can say something about the existence and the strength of the dark matter wake by looking at the wake in the stars. So what about our second question? What about fuzzy dark matter? So I'm going to switch back to our dark matter particles only. I've got cold dark matter on the right, and now fuzzy dark matter on the left. And hopefully, you can see why fuzzy dark matter is called fuzzy. This is not a resolution effect. These are these density granules that show up due to the wave interference between particles. And they kind of just get amplified in the wake. And so at small scales, these look pretty different, but at least on large scales, if you look at like the size of the contour, for instance, it's pretty darn similar. So the next question is, can you see it in the stars? Here we have cold dark matter. And here's the stars in fuzzy dark matter. And so at least in the density of the stars, these do look pretty similar. So at this point, if you're only looking at where the stars are, you know that the dark matter wave is there, but you don't know what it's made of. And so if you want to find out what it's made of, yeah.
So how are the dark matter particles, the star particles, like implemented in your code?
Yeah, so in the cold dark matter case, it's n-body. So I
And
should
there's
say
no difference between the star particles and the dark matter particles in terms of.
the density is different, the velocity dispersion is
Okay,
different.
got it.
Yeah,
That's-
the stars are always test particles because
Right.
there's like 8 orders of magnitude less stellar mass in this box
Got
than dark matter mass, so it just makes the calculation go faster.
So when you're saying like self-gravity, like the dark matter particles are allowed to interact with each other, and the star particles feel the effects of the dark matter, but not each other.
Correct. And then when I say no self-gravity, all of the particles are test particles, they only feel the LMC. Yeah,
So in any of your fuzzy dark matter simulations, if you're changing the velocity at which the particles are streaming past the LMC, do you see any of that density weight in the front of the LMC?
gotcha. So at the speeds the LMC is moving, you wouldn't expect to see that pile up.
I see.
We also don't change, we did look at like a slower case that was meant to mimic when the LMC was like further out, like at the outskirts of the Milky Way, and yeah, we still didn't see any of that density before we run. So that you would expect the LMC's orbit to be the same in models. Cool. Yeah.
Yeah, how did you know that the bulk velocity of the stars in the dark matter the same, like in your wind tunnel?
Yeah, so this is all assuming that that the wind tunnel speed is set by the speed that you would expect the LMC to be moving through the dark matter halo and the stars. So assuming that those components of the Milky Way don't have any like preferential velocity with respect to each other, then you keep the width the same. Yeah. Cool. Anything else? I was told in the pedagogy class once that if you pause longer for questions, sometimes. Okay, so the takeaway here is, at least if you're only looking at the density of the stars, again, you can tell the dark matter wave is there, but not necessarily what it's made of. So in order to try to distinguish between these two scenarios, instead you can start looking at the velocities of the stars, the kinematics. So what I can do is I can take all of the stars within these wakes, I can measure their velocity dispersion with respect to the background wind. And I can put that on a plot that looks like this. So again, this is the velocity dispersion of the wake relative to the background for the stars in each of these 3 models. And so cold dark matter without self-gravity here, again, only gravity on these is from the LMC. If I add the gravity of the dark matter wake, you can see this goes up a little bit. And that makes sense, right? If you have more mass deflecting the stars, you're going to get larger deflections, higher velocity dispersion. And so that's really cool because that means not just in the density, but the dark matter, what's going on with the dark matter changes the kinematics of the stars as well, and not just sort of where they're located in the halo. So if I add fuzzy dark matter, you'll see this goes up again a little bit. And that is again because of the interactions between the stars and these granules. The stars scatter off of these granules in the wake, and that provides an additional source of heating for the stars. So I will point out that the dynamic range here is not that large. If you convert that back into physical units, the difference between the bottom of the plot and top of the plot is like a hair over 3.5 kilometers per second. So these are not huge differences. We have shown that if you can measure enough stars, these should still be detectable differences with like current spectroscopic survey errors. But the trick there is getting a good handle on what the background dispersion should be. That's going to be a lot more difficult. But again, I think the main takeaway here, even though this is probably difficult to observe, is just that there's probably information contained in the velocities of your stars as well, as opposed to just the densities. So it's a good reminder to sort of look at all of the information that you have available to you when you're trying to discriminate the small ones. Yeah.
Another kind of just annoying complication.
Oh
I don't
gosh,
know.
no, I still look guilty about that.
No, we did this to be in a talk, and like, I know, things are complicated, shut up.
It's supposed to be.
But is that LMC and the SMC, is that a binary?
Yes, it is, yes.
So is that going to, yeah,
You gotta start simple.
yeah,
If you use the entire kitchen sink at once, you have to separate your forks from your plates from your spoons from whatever.
you're,
If you just look at plates for starters, you got a much better idea of what's on.
so I was thinking like as the SMC.
Oh, yeah,
kind of
totally.
working, the
So-
concept
so-
of mass, you're just gonna kick off and the velocity dispersion increases.
Oh, it's gonna go crazy,
Yeah.
right. I would love to be able to do that whole three body thing in fuzzy dark matter. It's just too expensive. It's that you need like some crazy resolution requirements to do the fuzzy dark matter correctly. And so these wind tunnels are really what we're limited to. I don't even think anyone's successfully put like just an isolated Milky Way fuzzy dark matter halo blocks before. So, yeah, anyways, that's what I wanted to mention about the paper. And then I was gonna close with just a few thoughts of like sort of where the state of everything is right now and what we have to look forward to. So in terms of people actually looking for this wake, went the wrong way. There are a couple groups making observations of the outer halo and plotting the densities of the outer halo. So in particular, Charlie Conroy's group at Harvard, and there was a nice paper by Keiko Bushimi and collaborators recently, measuring the distribution of like K-giants in that outer halo and plotting their densities. And in both cases, you can see the wake shows up very nicely, trailing the LMC along its orbit. And so, at least the wake's been found, there aren't enough stars in these studies so far to be able to definitively say that, yes, we've detected the dark matter wake underlying it. But both groups are working on getting observations of more stars. They're also working on taking radial velocity measurements for the stars. And again, that gives you that kinematic information that can be really important for telling what's going on. So that's the state of the wake. I do think I would be a little bit remiss for not pointing out that in 2024, we have probably ruled out fuzzy dark matter as being like the only contributor to the dark matter. So this is a collection of like recent constraints on the fuzzy dark matter particle mass in the literature. Rubin put this together. And for each study, the red block shows you the sort of excluded parameter space. Yeah.
Wait, so we're saying that you can have multiple types of dark matter? Like that we don't have to have one dark matter particle, okay.
Yeah, and in my personal opinion, that's probably what's happening. But again, you gotta start with just.
Oh, yeah, I agree, like I've just never heard about it.
Isn't all dark matter ruled out? Oh, this is just the fuzzy.
No dark matter, you gotta start first.
Electron, so we're going from 10 to the minus 26
Okay.
to 10 to the minus 16.
Big mass range.
But like, I mean, if you compare that to like, classical WIMPs were supposedly like few hundred GeV, that's like
Right.
orders of magnitude. So this is just fun. And the basic sort of problem here is that you want the fuzzy dark matter to be light enough that it produces the right density profiles in dwarf spheroidal galaxies, but you don't want it to be so light that it starts messing with small scale structure too much as measured with Lyman alpha. You don't want it to raise the velocity dispersion of your dwarf galaxies too much. So at least this sort of very basic like fuzzy dark matter model has probably been ruled out, but there has been sort of increasing interest in a couple of basic modifications. These all have like particle physics motivation. So the first is sort of a two-component model where instead of having a single mass of fuzzy dark matter particle, you have two species, one with a large mass, one with less mass. And you see that the sort of light particle sets the overall structure of a halo. And the heavy particle can kind of help smooth out some of these really large granules that the light field produces, and that can sort of help alleviate some of this like catch-22 problem. Sorry.
Yeah, wait, this is the point of lunch seminar, to have a casual question talk.
This is so much more fun than me just like standing here and talking at a bunch of blank faces.
I haven't been to one of these talks in ages, so you're getting all the questions. All of it. So so if you have a multi-component mass dark matter, do you get mass segregation in your dark matter? But the heaviest is at the center. This goes back to your undergrad work.
It does, it does. You know what, I'm pretty sure you do. This is the paper to check out that like investigated these structures. I can't remember what the exact result was off the top of my head, but this is what they were looking at. And like, it's the relative, like which field formed what part of the halo that previously said, so.
That's good.
It's fun. Thanks. So the other thing you can do, is a self-interacting fuzzy dark matter. So if you have a very, very small, attractive self-interaction between these fuzzy dark matter particles, the amount of structure that you form, as you can see in these simulations, the blue arrows are the subhalos, it very, very sensitively depends on the strength of this self-interaction. And so you can sort of use that to tune the amount of structure that you're making as well. So that's the sort of state of fuzzy dark matter. With regards to the observations, again, this is just like a handful of the upcoming facilities that start doing this kind of work. But in particular, these surveys like Rubin Observatory, Roman Space Telescope, they're going to start taking deeper observations of wider fields at a higher cadence in the halo, and that's giving you more and more information on more and more stars. And I think that's really the bottleneck of where we're at with the constraining power in these dark matter models is we just don't have enough stars to really say something statistical about the differences between the dark matter models, at least in the outer halo. So hopefully that's coming very soon. I'm very, very excited for that. And yeah, that's pretty much everything I had. I think I'm like way over my half hour, but good discussions. I'll just leave the summary points up there for you to read whenever. And please ask more questions because I'm having a good time.
Yeah, no, we tell you 30 minutes so that we have time
Got
for
it.
all of that. So
Okay.
you are
Yes.
perfect on
Please.
time.
Yeah, I thought this was a really neat talk. I learned a lot. I had a quick question on your slide 26.
26.
Yeah, this one here. So the absolute scale of the thing here, so is this saying like the stellar wake has the capacities for doing 17%-ish of the stars outside? Just
Yeah, 17% higher.
30% higher.
Yeah, the wake's hotter than the.
That's what I was confused about, but I see.
Gotcha, sorry, yeah.
No, that's fine.
Yes. You're on the line, sorry, it's already.
She said the difference in the velocity of the cell is something like 3 kilometers.
Something like that, yeah.
Would you be able to, without including the SMC in your models, be able to conclusively say whether or not the dark matter wave was contributing to it?
That's I think the really hard part of making that observation, again, is not necessarily, like, from a pure statistics standpoint, given the typical measurement errors of these spectroscopic surveys, if you had a perfectly smooth stellar halo with enough stars in the wake somewhere around 900, you could make that measure. The problem is not measuring the velocity dispersion inside the wake, it's measuring the velocity dispersion outside the wake. Because the real halo is not this very smooth spherical collection of stars. There's a lot of structure, the SMC messes with things, there's stellar streams. So I think that's the really hard part of that measurement, is in order to get this relative, right? you need to also know the background. The background's a little harder to get a handle on.
Can you do the same experiment, so you say that fuzzy dark matter is probably kind of ruled out as being the major contributor?
Sure, yeah.
Can you do the same experiment with different, like, with particle sizes or different types of warm dark matter versus?
Yeah, so you totally could. The only thing with that is, I don't think the wake would change much, in all honesty. Because at the end of the day, the only thing that's really different with the fuzzy dark matter is the fact that you have to take this wave interference, like there's the.
Not to the extra
part.
5%.
Yeah. Whereas with, like even self-interacting dark matter, like the densities just aren't high enough that the scattering really matter. And the warm dark matter at the end of the day is just another NP calculation.
Yeah.
So I really think that fuzzy dark matter is the only thing where you're really gonna see a big difference. That's why we went with there. We went like, if you don't see it with this, you're not gonna see it with any difference probably. Yes.
In one of the slides, I think the one where you ruled out the fuzzy dark matter, you mentioned, I mean, there was Lisa in one of
The starting when you see it.
when you ruled out fuzzy dark matter,
Oh, yeah.
that's way ahead.
Raw direction.
I'm just wondering what the frequency scale is if we were to look for gravitational wave signatures of fuzzy dark matter, whatever that's called.
That's a really good question. I'm not gonna know that off the top of my head, sorry.
So, I mean, it says Lisa with the 2018.
Yeah, yeah. I would have to remind myself what that paper says, sorry. Anybody else?
Awesome. Well, next week we have a Zoom talk from Hayden no, you're Hayden, Nicholas Saunders. I was like, I mixed up the two names. Nicholas. No, his name's Nicholas. Nicholas Saunders from Hawaii, so he's gonna join on Zoom, but we'll still have pizza and like gather here and all watch